cool. So it's great pleasure to have Kwok Wai Chan from Hong Kong. He's going to tell us about the quantization of Kahler manifold.
Okay, thank you very much. So I want to thank Satoshi for inviting me to give a talk in this very interesting seminar series. Okay, so I'm going to talk about quantization of Kahler manifolds, which is a recent topic in my research, joined with Conan, Leung, and Chin Lee. So you can just find the series of papers on the archive we put this year. And there are 4 papers, but the latest one is just a survey of the previous 3. Okay, so let me start. So actually, the motivation, well, first of all, I'm new to this topic. So maybe, I don't know, maybe there would be something wrong, misunderstanding about the theory, or some mistakes. So just feel free to point it out if you find that what I'm talking about is wrong. Okay, so so quantization is a process that I think very familiar to physicists and also a lot of mathematicians. So roughly, it's just a procedure which produces a quantum system from a classical system. So in a way, we regard the classical system as an input, and then we want to cook up a quantum system. So I think in the talk today, I'm going to focus on just classical mechanics and quantum mechanics. So so in that situation, a classical system is formulated as a so maybe let me make use of my pen. So a classical system is formulated as a symplectic manifold. So X is a smooth manifold of even dimension, and omega is just a symplectic form. Okay, namely just a closed non-degenerate 2 form on the manifold X. And then there are various methods, I guess, of course, motivated by the discovery of quantum mechanics. Then physicists and as well as mathematicians started to figure out ways to do quantization. Okay, so they want a very systematic way to do this process, and there are various methods, very well-known methods right now. The first one is called geometric condensation. So that is pioneered by Kirillov, Korsten, and Schrull, and then I think it's in the 1960s, something like that. And the second approach is called deformation condensation, and this was first proposed in, I guess it's a series of 2 important papers in the 1970s, maybe late 70s, by Berezin and his collaborators, a bunch of mathematical physicists. So they so the point of focus is a bit different in these 2 approaches. So in geometric condensation, as we will see, we want to cook up a Hilbert space and then also quantize functions as quantum as operators on the Hilbert space. But in deformation condensation, it's like we go right away to the space of operators, or the space of quantum observables. And okay, so maybe let me not talk about quantum theory today. Okay, so so I guess that is like the point of contact of my work with physics. but maybe from this point on, my talk will be mainly mathematical. Okay, so let me try to briefly review these two approaches, the two main approaches that I want to talk about today: geometric condensation and deformation condensation. Oh, well, before that, I have a chart here summarizing what we want to do. So, so condensation roughly means this is like a chart I copied from Kukhov's paper. So, so in general, we want to start with this symplectic manifold, X and omega. We want to associate to it a Hilbert space, a vector space with an inner product, and then for the space of functions, we want to quantize it to an algebra of operators, or what we call the algebra of quantum observables. So for every function f, you associate an operator called OF, which is an operator on the Hilbert space, and even further. So there are many structures that you can quantize. For example, Lagrangian submanifold, you can quantize it to be a vector in the Hilbert space, symplectomorphism to be automorphism of the algebra of operators, and so on. Okay. So so let's start with geometric condensation. So so again, the input is a symplectic manifold X and omega. And to start this process of geometric condensation, we need to first assume a so-called pre-quantum condition, namely the omega is an integral class. Okay, so if omega is a closed two form, so it defines you a the Ram cohomology class, and then the condition is that this class has to be integral. So has integral coefficient. And this condition actually tells you that there exists a line bundle, a complex line bundle over X, together with connection, such that the curvature up to a constant is just the given symplectic structure. Okay, so that is the pre-quantum condition. Okay, and if you have this data, so it is like what Carsten call a pre-quantized symplectic manifold. So X omega together with this line bundle and also a connection. Then you can look at the space of L2 sections of the line bundle, or even more generally, you can look at the tensor power of this line bundle. So let's say you fix a positive integer k, and then you look at the L to the tensor k, and look at the L2 sections. Okay. So well, if X is compact, then of course you just look at all the smooth sections, because L2 is just a condition you impose so that you can integrate. Okay. And then there is a very subtle process called choosing a polarization. So I will give you some examples of this in a moment. So if you choose a polarization, then you can determine the Hilbert space, which is now a subspace of this space of L2 sections. So the issue is this space of L2 sections is usually too big for physical purposes. At least that's the story that I heard. And we have to find a way to cut down the dimensions of this, or cut down the size of this space. And choosing a polarization gives you a way to somehow cut down the size to half, okay, of this subspace, and that will actually gives you the Hilbert space that you need in physics. Okay, so let me go through a couple of examples. So first of all, let's say we look at this very simple symplectic manifold that I think everyone will learn in the first course on symplectic geometry, which is the cotangent bundle of the manifold. So M is just an arbitrary smooth manifold, and then you take the cotangent bundle, and then the cotangent bundle is naturally a symplectic manifold because we can equip it with this standard symplectic structure. So so here So here, this dxj, so xj are like coordinates, local coordinates on M. You just choose arbitrary coordinates. And then this pj's are coordinates on the fibers. Okay. And in this case, well, for example, in particular for physical purposes, I think the most interesting case is when M is R3. And then that gives you the classical phase space for mechanics. And in this example, you just take the Hilbert space to be the all the functions on M. Okay, so we take H to be the space of all L2 functions on the smooth manifold M. At least in the case when M is R3, that's what we need to consider in mechanics, right? So so somehow it's like physics tell us or teach us that the Hilbert space should be L2 of M. But in the context of geometric condensation, you should think of this Hilbert space, this L2 of M, to be functions on X. Okay, X is the cotangent bundle, but which are constant along the P directions, so along the fiber directions. So that's why they are like functions on the base. Okay, because these are functions on X which are constant along the fiber directions. Or in other words, using somewhat more fancy language, you can say that this H is the space of all L2 sections of a line bundle, which is nothing but the trivial line bundle L over X, which are covariantly constant along a distribution or along a subbundle, okay, along a half of the directions in the tangent bundle. So what is that subbundle D? D is nothing but the subbundle generated by the vector fields along the fiber directions. Okay, so these are like the vertical subbundle of this tangent bundle. Okay, so this is the polarization that we refer to, and in this case it has a special name. It's called a real polarization. So let me repeat. So the Hilbert space H in this example, the cotangent bundle of M is nothing but the space of all L2 sections of the trivial line bundle. Well, if you have trivial line bundles, then of course the L2 sections are nothing but the L2 functions of this X, which are covariantly constant along this distribution or this subbundle. Okay, so this is the situation for cotangent bundle of M. And so this gives us an example of a real polarization. More generally, you can look at Lagrangian fibrations on symplectic manifolds. That will give you, or even more generally, you can look at Lagrangian foliations of symplectic manifolds. That will give you more possibility of real polarization. But
I have one question. So this Kahler L is equal to X times C, you mean?
Oh, yes.
Okay.
Thank you. Sorry. Yeah, this is X, not L.
Okay.
Thank you. It's the typo. But I think for those who know this theory of integrable systems or real polarizations, you know that the interesting cases are when the fibrations have singular fibers, which we don't see here. But anyway, that's not the focus of today's talk.
But yeah, this Kahler L is not the pre-quantum line bundle. You
can choose a connection on L whose curvature gives you omega. Yeah, it's a trivial bundle. In this case, the symplectic structure is exact. So it gives you a trivial cohomology class.
I see. Okay, thanks.
Okay. So this previous one is the real polarization. And there is another very typical type of polarizations called complex polarizations. That's when your manifold X admits a complex structure, okay, which is kind of compatible, with the symplectic structure. So actually, that lead us to the realm of Kahler geometry, which is the topic of today. So in case X is a Kahler manifold, which is just as I said, a symplectic manifold together with a compactable, integrable complex structure, then you can take the complex polarization. And actually what is complex polarization in this case is now you relax the definition of polarization. You don't just need to look at a subbundle of the tangent bundle. You also look at the subbundle of the complexified tangent bundle. And a complex structure, actually an almost complex structure, is nothing but choosing a half-dimensional subspace or subbundle inside this complexified tangent bundle, namely the T10. Okay, so that's specify the holomorphic directions, and here you just choose this subbundle. Okay, so any almost complex structure is given by such a subbundle, but the fact that the complex structure is integrable is equivalent to saying that this D sub C is a polarization. Okay, because you need the integrability condition. That is exactly equivalent to the fact that the complex structure is integrable. Okay, so in this case, well, at least when X is compact, then actually the pre-quantum line bundle. So remember, that's just a complex line bundle with a unitary connection, and the curvature is omega. The pre-quantum line bundle becomes ample, or what we call positive. Okay, so you can imagine that the line bundle has positive curvature, and then by Kodara's embedding theorem, you know that X is actually a complex projective manifold, so it's algebraic. Okay, so it's defined by polynomial equations, and in this case, you take the Hilbert space to be again. It's like the general construction of the Hilbert space for any given polarization. You just take the L2 sections of the line bundle, which are covariant constant along the directions specified by the polarization. Okay, so in this case, you just take the sections of L, which are constant along this T10. Okay, but that turns out to be just the space of all holomorphic sections. So that is like the holomorphic sections, this line bundle L over X. Okay, and so in the case when X is compact, you know that it is a finite dimensional subspace in the space of all L2 sections. Okay, so this gives you two typical examples in the case of geometric condensation. Now, how about deformation condensation? So as I mentioned at the very beginning, deformation condensation is like skipping the step of constructing the Hilbert space. So it jumps right to the construction of the algebra of operators, or actually it's not operators. So it just constructs the algebra of quantum observables directly. Okay, so that is H bar. Well, H bar, mathematically, we always regard H bar as a formal parameter, and this H bar is supposed to depend on this H bar, and so from the viewpoint of deformation theory, it is just nothing but a formal deformation of a certain algebra. So actually. I think Bayer and his collaborators, what they propose in their paper is that you can directly construct the space of quantum observables as a formal deformation of this commutative algebra of functions on X. Okay, so you just look at this space of functions, vector space of functions on X, and then the product is just the pairwise modification. This is a commutative algebra, and deformation condensation is really, you can regard it as a mathematical problem. You just want to construct AH bar as a deformation of this commutative algebra. but there is a restriction, of course, because we want it to be kind of related to physics. So we want to recover the boson bracket, which is, I think, a very important structure in physics when we talk about physics associated to a symmetric manifold. So we want the boson bracket to be recovered as the first order term of the commutator of this product. Okay, so we deform this commutative product dot into a non-commutative product called star, and actually people call this star products. Okay, so the requirement is that the commutator of this non-commutative star product is has a so the leading term is just the original dot, but then the first order term is like if you compute a commutator, you will recover the boson bracket. Okay, that's one of the requirements. There are several others which I'm going to skip here. Okay, so that's the deformation condensation, and that makes quantization looks like a very much like an algebraic problem, and very mathematical. Because of this requirement, this is the most essential requirement. You can actually study deformation condensation for boson manifolds as well, not just for symplectic. And if you look at the history of this problem, you will see that there is a huge difference when you try to prove the existence of deformation condensation for symplectic and boson manifolds. I mean, the symplectic case was known, I don't know, maybe in the early 80s by Fedosov and also another group of mathematicians. But the case for boson manifolds was not known until Kontsevich proved the existence of the deformation condensation in 1994, I guess. Okay, and that's also one of the reasons why he got the Fields Medal. Okay, so why don't I go through again a couple examples for you.
Before
yes.
that, let me make some physics comment in this the story. So because there is a physics audience in the so this general quantization is often appears in this the constructed Hilbert space of Chern-Simons. For instance, band G using a modulus for G bundle, modulus of real flat connection real bundle to construct on a Riemann surface to construct a Hilbert space of the Chern-Simons or conformal block of Westminer-Witte model. Whereas deformation quantization is often recently appears a quantization of Coulomb branch and Higgs branch of superstring gate theory, where this H bar is really corresponds to omega background. So that if you turn on omega background, the operator that will give you the coordinate ring of the X, symplectic manifold or Coulomb branch, becomes non-commutative due to the omega background. So that for instance, 3D NQ4 monopole operator becomes non-commutative. That will give you the algebra of the holomorphic function over the Coulomb branch and Higgs branch.
So why don't we consider deformation condensation in the case of Chern-Simons?
Deformation quantization, Chern-Simons, we are not going to consider the deformation quantization Chern-Simons, but we consider deformation quantization 4-dimensional n equal to 2 Coulomb branch, which is related to Hitch moduli space.
Yes.
And in Hitch moduli space, there is a Lagrangian submanifold in band G. Band G, whether you can have the German quantization, Hilbert space. So you can construct the algebra out of the Hitch moduli space that acts on Hilbert space that come from band G, which is Lagrangian submanifold.
Okay, I see. Yeah, that's exactly what I want to talk about.
Okay.
No. I don't mean the example that you're talking about, but the topic of my talk is about the relation between geometric condensation and deformation condensation.
Okay. So I just want to make
one physics comment. Yeah, but it's good to know your example.
Okay, so
I mean, the example that you mentioned, yeah, it's
so
very
that's
good.
one physics one. Please go ahead.
Okay, thank you. So, right. Okay, so I just wanted to mention a couple very simple examples. So again, the first example is given by cotangent bundle, but in this case, we look at the really flat case. So let's say the cotangent bundle of Rn. Okay, so that's very familiar for everyone. So remember in the deformation condensation, we just want to cook up the algebra, okay, the non-competitive algebra. So how do you do that? That is, I think it is called the Moyar product, the Moyar construction. So well, first of all, you look at the function on x. X is just the cotangent bundle of Rn. And let's say your f depends on the fiber directions in a polynomial fashion. Okay, so so more precisely, you can take f to be like a section on Rn of this symmetric power of the tangent bundle of Rn, but you can just think of it as a function of x and p, but the dependence on p is like a polynomial. Okay, so if in that case you can easily quantize f, because you just observe that f is a symbol of a linear differential operator f hat, where for the x direction you just treat it as multiplication, just ordinary multiplication by x, xj, but then you treat the fiber variables pj as pj hat, which is like differentiation. Okay, so I guess the physics terminology is like the xj is like a creation operator. This pj is like the pj hat is like the annihilation operator, something like that. Okay, so pj hat is just differentiation. Okay, so for this type of functions, you just quantize it in this way. So you have a map from f to the space of differential operators on Rn. Now, you just take the composition of differential operators on Rn, and then you pull it back. You go back to the function. That defines you the star product in this case. So that's called the Moyar product. And that's I think the simplest non-trivial example of this deformation condensation. And the condition that the first order term of the commutator, this star here, is the boson bracket is nothing but the uncertainty principle. Okay, so that's I guess that's very easy to understand and really close to physics. Okay. Now, on the other hand, for the same x, we can view the same x. So x, remember x is the symplectic manifold, which is just the T star Rn. Okay, sorry for my handwriting. We can as well view it as Cn. Okay, so because it just amounts to choosing a complex structure on this vector space, because as a vector space is just nothing but R2n. Okay, so you just choose a complex structure that makes x into this Cn. Okay, you can say we are choosing like a linear complex polarization. Okay, now if you apply geometric condensation using this complex linear complex polarization, in this example you will get this Hilbert space. Again, the L here is just the trivial line bundle, but actually this gives you a very well-known space, which is called the Bachmann-Fock space, I guess. I didn't write here. Okay, what is that? So that's nothing but the space of all holomorphic functions, which are L2 with respect to this inner product. Okay, so it's like the Gaussian measure, the ordinary Gaussian measure. But if you raise L to the power k, then you just multiply this exponent by k. Okay, so this is a well-known Bachmann-Fock space. I think everyone studying maybe quantum mechanics on Rn will have seen this before. Okay. On the other hand, for deformation condensation, you can play the same game as the previous Moyar construction. But now here, we call this the Wick construction, the Wick product. The Wick product. So I forgot to write down the names in this page. So this is the Wick product. If you know the name, then maybe it's easier for you to understand. Very similar to the previous one. So we, for every f, now for every smooth function f, for simplicity, assume that it's a polynomial. Now you have both the holomorphic and anti-holomorphic directions. So z and z bar, right? What I mean is zj and zj bar, okay? J from 1 to n. Now you can easily quantize it to be an operator. And in this case, the holomorphic variable acts as the creation operator. And the anti-holomorphic ones act as the annihilation operator. Okay, so the zj bar, you quantize it as a differentiation. Okay, now again, you map all the functions, or at least all the polynomials, to the space of differential operators, and then you use the composition in the space of differential operators. You put it back. That gives you the star product, which is what we call the Wick product. Okay. And then in this example, in the example on this page, you can observe a very nice phenomenon. Namely, well, first of all, this f hat. So let me go back. This f hat, namely zj x by zj multiplication with zj, zj bar x as a differentiation with respect to zj. So this kind of quantization process can be viewed as what we call a Topless operator. Okay, so what is that? So that is nothing but so f hat can be realized as this T f comma k. And what is this? It is actually a composition of two maps. The first one is mf, which is multiplication by f. And the other one is this projection from the space of all L2 sections onto, orthogonally, onto the space of holomorphic sections. Okay, so this is known as Topless operators. I think it has a very long history already. And a lot of people study this kind of operators, mainly on the analysis side. Okay, however, the point that I want to make is that now you look at this space of all polynomial functions on Cn, or more generally, all analytic functions on Cn. Okay, so actually you can extend this construction to analytic functions on Cn. So C omega here means analytic functions on Cn, and then equipped with this star product. So this is the deformation condensation of Cn, right? And we have an action here by this Topless operator on the space of on the space of holomorphic sections. So this H is nothing but the Bauman-Fock space. So it's you can regard it as H0 of X, the trivial line bundle tensor to power K, the space of sections of this line bundle. Okay, so it is known as the Bauman-Fock representation classically.
So a question is,
yeah,
the norm in the L2 space is not the usual, but also is the Gaussian part, right?
Yeah. But yeah, you're right. So yeah, we have this Gaussian measure here. But I think that it is this was studied very long time ago in the context of quantum mechanics, Bauman-Fock representation. Okay.
And also, do you need the normal ordering of the operators if you do the Fourier transformation? You change the.
Oh yes.
Yeah, you need to put all the differential operators in the right hand side to the normal ordering.
Yes. I guess we did, yeah. I guess we do need the normal ordering here. So kind of like you push all the holomorphic variables to one side and holomorphic one to the other side, something like that.
Okay.
Yeah.
Thanks.
Okay, so now the question that I want to ask is a very naive question. So the question is the following. So if you have a Kahler manifold, then actually you can construct a similar, well, in exactly the same way, this Topless operators. Okay, so namely, if you have a smooth function f on the Kahler manifold, you just first of all you multiply a holomorphic section of the tensor power of a line bundle L by f. Okay, and then you will get a smooth section, not holomorphic anymore, but then you project it back. Okay, so that is the usual construction of the Topless operators on a Kahler manifold. And that is related to deformation condensation on Kahler manifolds because of this theorem by Bodeman and also his collaborators. So it's a very famous result. I think it goes back to 1994, something like that. Yeah. So the statement is that they obtain very precise estimates of the Topless operators. So they look at the composition of the Topless operators and then compare it. So they want to say that the composition nearly defines you a star product. Okay, so the statement is that there exists bidifferential operators Ci, so that and also constant, so that the difference between this composition and this series is bounded. Okay, and that defines you the star product for a general Kahler manifold. So in particular, that solves the question of the existence of deformation condensation on any Kahler manifold. Okay, so that's the well-known Berezin-Toeplitz star product, and we denote it by star BT. And then the algebra, we call it the Berezin-Toeplitz deformation condensation. Okay, so that is I think it's very foundational result in the deformation condensation of Kahler manifolds. Okay, now the question that I want to ask is this. So it's very simple. So in this flat case, we have this Bachmann-Fock representation. So my question is just simply, do we have an analog of the Bachmann-Fock representation in the Kahler case? Or in other words, do we have an action of the deformation condensation on geometric condensation, just like in the flat case? So in the flat case, we do have that. But for a curved manifold, like a Kahler manifold, can we cook up such an action? And if you look back at this estimate here, it tells you that it's not possible for a fixed tensor power k. Okay, so the problem is if we gather all the information of this tensor powers of the line bundle L, can we really cook up a representation? So that's somehow a question that we raise when we started this study.
I have one question. So,
yeah.
So in this flat case, when you construct Hilbert space, do you use entire manifold X or Lagrangian submanifold? No, or flat case.
Sorry, can you say again? Yes.
So when you construct the Hilbert space X by geometric quantization, do you use entire Kahler manifold X, or do you pick some Lagrangian submanifold? So this X is C to the N, right?
Yeah, X just C to the N, yeah.
And
so
then you just
so
consider,
we pick so we construct the Hilbert space using geometric condensation. So we just pick a complex polarization, which is like a
over entire
so
space.
that's just a but that's just a complex structure in this case, and a complex structure in this case can be regarded as choosing a subbundle, like oh sorry, like this T10.
That I understand. That I understand. That's you
Yeah.
just
So
pick
so
one more
T10
perspective.
you can regard it as a Lagrangian in some way.
Okay.
And actually the polarization, the definition of polarization is like a Lagrangian subbundle.
That I understand. That I understand.
Yeah.
Okay.
Is that the Lagrangian that you're
Okay.
referring to?
But can you put the algebra structure on this H0? Instead of the
yeah,
Hilbert space, vector space.
actually we are looking at the algebra structure. Yeah. Right. So this is the Bauman-Fock space, but at the end, we are actually taking a formal power series version of this, not the analytic functions.
Okay.
So at the end, we are going to go formal and make everything algebraic.
Okay. So in that sense,
So
your algebra A sub H bar is isomorphic to this Kahler H Hilbert space as a vector space, you mean? Is it true? So when can you insert algebraic structure with H and so that it becomes
AH is this AH bar is like a subalgebra of this automorphism here, right? Not automorphism, the endomorphism.
End of H. Okay.
Something like this, right?
It's a subalgebra.
Yeah, actually, the differential operators on this it's like a differential operator on Cn. So actually this is like the algebra is like a subalgebra of this differential operator on Cn. The AH bar is like something like this, a subalgebra of this algebra of differential operator on Cn.
Okay, but Cn is not H, right?
Cn is not H. Yeah, Cn is not H.
Okay.
Yeah, H here is infinite dimensional.
Yeah, that I know, that I understand. Okay, thank you very much.
Okay, yeah. So the question that I want to ask is just, can we have an action of deformation condensation on geometric condensation in this curve case, the Kahler case? Or you may think of the flat case as the local case, near a point. And can we extend such an action globally? So that's the question that we want to ask. But here is a remark. Actually, Gukov-Witten say that the deformation condensation is not a condensation. Because they say that in physics, if you really want condensation, then you need not just formal condensation, but actual condensation. They somehow suggest that deformation condensation is just mathematical.
No, it's also mathematical. It's
you agree?
physical. Okay, anyway, go ahead.
Yeah. So, but our answer to this question is somehow justifying that deformation condensation can really be regarded as a condensation. Okay, so how do we proceed? Well, first of all, you notice that, remember, we have this tensor power of the line bundle L, okay? So, and actually, what is H bar? H bar is, we should regard it as 1 over K, okay? So, in the classical limit, you are thinking that H bar is going to 0, okay? So that means K goes to infinity. So if we let K go approaching infinity, then we should be approaching the classical limit. And in geometry, or in the Kahler geometry or mirror symmetry, there is a term called large volume limit. Okay, why this K goes to infinity is related to large volume limit is because, as I said, in the Kahler case, because the line bundle L is positive, so it allows you to embed your manifold X into the projective space, and then you can pull back the Fubini-Studio metric from the you can restrict the Fubini-Studio metric to X, and then gives you some Kahler metric. Okay, if you let K goes to infinity, then this metric or this symplectic structure is going to the so-called large volume limit in symplectic geometry. But in any case, the geometry looks like very much like the Fred case then, and this locally around a point. So if you look at locally around a point in this X with equipped with the symplectic structure K times omega, and imagine the K is very large, then you are getting closer to the case of the Fred space, okay? But technically speaking, so this is like a conceptual way to explain our idea. But technically speaking, what we are really doing is like we localize the sections of this L tensor K. What do we mean by localize? What we mean is that we want some sections which concentrate near the point x0. So this line bundle has a norm, has a metric here, and then we can define a norm for the sections of this L to the power K. And we want the norm to be concentrate near x0. And actually that's using a key idea in symplectic, in Kahler geometry called peak sections. So that's, I think that this term was invented by Tian in 1990, maybe in his thesis. So he could really cook up some sections, holomorphic sections of this line bundle, which look like a bomb sections. Okay, so it's really like a bomb section whose norm concentrate near this x0. And then and moreover, you can the norm or maybe the section, the leading order term of the section looks like a monomial. Okay, so that's why it's possible to give us a model of the space of all sections by this power series space. Okay, so so somehow I'm sorry I cannot explain more details here because it will go very technical. But the idea is just localizing these sections of this L to the power K using peak sections, and then that will allow us to define Hilbert space, which is infinite dimensional actually. Okay, so the Hilbert space is associated to a point x0, which we fix at the very beginning. And what is that? That is taking this huge tensor, a huge product, huge direct product of all the sections of this L to the power K for all K, okay? But then there is a equivalence relation, which we define using estimates of the peak sections, okay? So in practice, actually this equivalence relation tells us how to relate sections of L to the power K for different Ks, okay? Because you imagine that if the tensor power K increases, you will get more sections, okay? So it's like this quotient or this subquotient actually is not. I'm sorry, it's a subquotient. We have to take a certain subspace of this product and then quotient. So this subquotient is somehow like an inverse limit or maybe direct limit. So when you tensor L to the power K for bigger K, you should recover sections of L to the power K for smaller K. Okay, so this equivalence relation captures exactly the relation between sections of L to the power K for different Ks.
Oh,
okay.
What is n is the dimension of the X?
Oh yes, n is the dimension. So
okay.
Yeah.
And
so,
X is projective.
Yeah.
Okay.
Yeah. Because actually, when you do geometric condensation for Kahler manifolds, then automatically you will you have to require that X has to be projective. Okay. So so this is also important. So at the end, the subquotient space, the Hilbert space that we define is actually isomorphic to this Fock space. So that is the like the Fock space or the formal Fock space. So that is like the formal version of the Hilbert space that we see in the Bauman-Fock action. Okay, so now here is our first main theorem. So we can actually prove that this x0 really gives you a representation of the Berezin-Toeplitz deformation condensation. So this algebra really acts on this x0, and the representation is local. So as you can imagine, and also I think locality is expected from physics. So the operator OF you associate to every smooth function is actually only depending on the infinite jets of the function f, or the Taylor expansion of f around the point x0. And also the representation is kind of minimal. So well, it's easy to see that it's not irreducible in the usual sense, but somehow we can modify the definition of irreducibility to a weaker version, and then we prove that it's irreducible in that weak sense. And actually this action is nothing but equivalent to the action of the Wick algebra. That is the Wick algebra, which is the space of functions or formal functions on Cn, on the flat space, on this Fock space, okay, or Bachmann-Fock space. So this is our first result. Actually, the main result in the first paper of the series. Okay, but now we want to do more. So so the question is, well, this construction depends on choosing a point on the Kahler manifold X, right? We choose X0. But we want to see how this X0 are related for different points. In other words, we have a point-wise representation. So we want to glue this together to give you like a sheaf version of this representation. So actually, this is also related to the work of, I think, Victor Ginsburg and his collaborators. Okay, so the question is, how are these Hilbert spaces, when you vary the point on the Kahler manifold, are related? So to see this, we mimic Fedosov construction of star products on a symplectic manifold. So that's a well-known construction of Fedosov. A well-known construction of star products is given by Fedosov. So the idea is like what I said. So so for a symplectic manifold, so here X is a general symplectic manifold, and then on the tangent space, on the tangent space of a point, you have this Moyat product, which is one of the examples I review when we talk about the deformation condensation. Okay, so the idea of Fedosov is very simple. So for each of this tangent space, we already have this star product. So why don't we glue them together? Okay, but of course you don't glue it in an arbitrary way. So geometrically you should glue it using a flat connection. Okay, so it turns out that this question boils down to solving so-called Fedosov equation, which is giving you a flat connection on the Weil bundle. So maybe I should write down what the Weil bundle is. So the Weil bundle of X is nothing but you take the symmetric power of this complexified tangent bundle. So Tx tends to C. Okay, so that is the Weil bundle that Fedosov used in his construction. Maybe you have to take some limit. I mean, completion of this tensor power, this symmetric product. But anyway, this is the Weil bundle. It's like the section of this Weil bundle is like a smooth. You have smooth functions on the base, and then you have some power series on the fibers of this tangent bundle. Okay, so so the key point is to cook up this Fedosov flat connection or abelian connection on this Weil bundle. And once you get this flat connection, you can define a map, actually a map in this direction. So which is called a symbol map. So so for a section of the Weil bundle, you just take the leading order term, you get a function on X. Okay. Now the point is, so the main result in Fedosov paper is that you get an isomorphism if you restrict to the space of flat sections on this Weil bundle. Okay, so in other words, given any function f, you can define a certain section associated to F, which is flat with respect to this Fedosov connection. And because on the Weyl bundle, you have it comes with a product, which is just the usual product on the Weyl bundle. So the star product is given by just pulling back this usual product on the Weyl bundle. That gives you the star product on the symplectic manifold. So it is a very geometric way to construct star products on symplectic manifolds. And so in order to understand how the Hilbert space X0 are related, we just mimic this construction. Okay, so well, first of all, when X is scalar, you can ask the question: can we now X is scalar, so the tangent space is naturally like a Cn. Okay, so the first question, even before we glue those X0 together, the first question that we can ask is, can we try to glue the wig products together on this tangent space of the Kahler manifold? Okay, so actually we can, and actually it is not we must not be the first to do it. So we saw a few similar constructions before us, but anyway, so we roll up our result in the, I think it's in the second paper in the series. So this is like a very formal statement now. So actually we can construct for any 1-1 type class. You can also you can always construct a solution to the Fedosov equation. So this is the Fedosov equation, and the meaning of this equation is exactly that the connection defined by this gamma alpha is flat. Okay, so that is actually equivalent to saying that df comma alpha square is 0. Okay, so it is just nothing but the flatness of the connection. Okay, so but why do we want to write up this result? It's because although there are similar constructions before, ours is still a little bit different. Actually, the main difference is that we are choosing a different gauge fixing condition in this solution of the Fedosov equation. So in particular, I think this point is quite interesting. Actually, we proved that this Fedosov connection gives us a way to quantize Kaplanov's area infinity algebra structure. So yeah, I think I don't have time to go into the details, but so one way to think of Kaplanov's area infinity structure is regarded as a connection on the Weyl bundle. But now in this case, the holomorphic Weyl bundle, not the complexified Weyl bundle, the holomorphic one. So it is Wx is the holomorphic Weyl bundle. So our construction of the Fedosov connection gives us a so-called quantum extension of this Kaplanov structure, in the sense that if you restrict the Fedosov connection to this holomorphic Weyl bundle, you recover the connection given by Kaplanov structure. So it is, I think this point alone is quite interesting. Okay, and I have just a few minutes left. So let me go back to the gluing of the X0. Okay, so the idea is to extend Fedosov idea. So now we have fiber-wise, we have this action, right? Wx0 acting on X0. So can we glue this representation together to give you a sheaf? Okay, so the result is that we can, so actually the idea is very simple. So we just construct a so-called Kwok bundle or Kwok sheaf, which is actually just the holomorphic Weyl bundle. So actually the ordinary Kwok sheaf is nothing but the holomorphic part of the Weyl bundle, and then you twist this Kwok sheaf by a certain line bundle. And there is some technicality there, because actually that's not a line bundle, because we want the curvature to be like 1 over h bar times something. and h bar is just a formal parameter. So we make a definition called a formal line bundle. But it's a line bundle thing, and after twisting by this formal line bundle, you get a fork bundle. And the important thing is, and at the same time, you can get a flat connection on this fork bundle. And then, and the first part of this third theorem is that this so-called Bachmann fork sheaf, which is nothing but the space of flat, the sheaf of flat sections of this fork bundle, but together with a convergent property. So we want to look at the analytic sections. Okay, so this Bachmann fork sheaf will be a sheaf of modules over this actually also a sheaf of flat sections of the wire bundle. Okay, so because the feathers of connection is kind of logo, so this space of flat sections of the wire bundle should be, I think it should be regarded as a like a structure sheaf of the quantum geometry of the symplectic manifold, quantum X omega, or the Kahler manifold. So so you may regard the feathers of construction as a way to construct the structure sheaf, and this Bachmann fork sheaf is like constructing a sheaf of modules over this structure sheaf. Okay, and the second part is saying that actually you can also define a certain subspace inside this stalk of the Bachmann fork sheaf, which is dense. And what is this subspace? This subspace is nothing but all the analytic sections. So locally around the point x0 is the same as all the analytic functions around x0, and they are like the coefficients of sections if you choose a frame in the line bundle. And then and finally, the action of these analytic functions on X acting on this dense subspace is by formal Topless operators. So actually the action is really by Topless operators. So yeah, maybe it's already too technical here. I am sorry about that. But the moral is that the answer to the question is yes, we can really construct an action of deformation condensation, at least in this case of Berezin-Toeplitz quantization on geometric condensation. But we have to take into account all the tensor powers of the line bundles, and also actually we just get a sheaf action. It's not really an algebra action. Okay, so yeah, so as I write here, this gives at least we guess a partial answer to the question that we raised at the very beginning. So I think I will stop here.
Okay, thank you very much.
Thank you.
Any questions from the audience?
Actually, I also wonder whether physicists will be interested in this question, whether you want to relate deformation condensation and geometric condensation in general.
So in physics, usually we pick hyperkähler manifold.
Yeah. Oh, yeah.
Hyperkähler manifold.
I think I should also mention that there is a very related work, which is the work of Kwok-Wai.
That's exactly what I'm working on now.
Yeah. So in that context, they proposed the brane condensation, and that also gives us a way to relate these two types of condensations. So yeah, as you said, it is in the hyperkähler case.
Yeah. So in physics, if you have enough number of supersymmetry, the modular space appears a hyperkähler manifold. And then if you do the deformation quantization of this hyperkähler manifold, you can construct algebra of the non-commutative algebra. And if you pick Lagrangian submanifold inside this hyperkähler manifold, you pick particular symplectic form, of course. then you can do the deformation, geometric quantization on this Lagrangian submanifold.
Yes,
And
yes,
this
yes,
algebra acts on this
geometric quantization.
Geometric quantization Hilbert space.
Yeah. That's exactly the proposal by Kwok-Wai, right?
Yeah. So, but in your setup, looks to me you don't choose the Lagrangian submanifold to create a module of this algebra.
One way to think about this. Yes. So in our setting, we have to choose a line bundle and then also a complex structure. So that's like a holomorphic line bundle on the Kahler manifold. But you can also put it into the context of the hyperkähler case. Namely, you take the cotangent bundle of X. That gives you a holomorphic symplectic manifold, which is very close to hyperkähler.
Yeah.
And then the line bundle should gives you a Lagrangian in this hyperkähler or holomorphic symplectic manifold. Yeah.
Yeah.
I think it's possible to compare these two settings.
Yeah. Yep. And I think some audience have question. Does the audience have a question? No.
Maybe it's time to go back to the election.
Kwok Wai, let me ask a question.
Hi.
You mentioned that Gukov and Witten claim this some quantization is not quantization. What precisely did they?
In some sense, it's quantization.
They say that they say that if you really want quantization, then you should have some convergence in the star products, and then you have to you need to be able to evaluate H bar to some real value, not just formal.
So that just means it's formal or analytic, right?
Yeah. So they claim that formal is not general quantization, but analytic ones are.
But in some sense, it's quantization, even physics. Yeah, it's really quantization. I mean, it depends on the definition of quantization, but even physicists, I would imagine Google who agree. I don't know, but
yeah, that's true.
Anyway, in some sense, it's quantization.
I think I read this comment in Gukov and Witten's paper.
Oh, okay.
The brain quantization paper.
Yeah. Any other question from audience?
So is it true that the quantization, or should it possibly be true that they can always be understood as a kind of path integral defined by path integral, just without regarding the convergence or not of the well-defined, but just some expected integral from the mapping space from S1 to your target?
Yes. So thank you for this question. So maybe I can mention something concerning this theorem too. So here we construct this feathers of connections, and actually there was earlier work of Seeley, Chinley, and also Grady. So they can construct from this feathers of solution a solution of the quantum master equation in the case of a sigma model from S1 to the target, which is the Kahler manifold here, X. So it's really related to quantum field theory, one-dimensional quantum field theory. In that case, it's a sigma model. So
is that supersymmetric?
I don't think they consider supersymmetry in that case.
Well, because I remember that.
But I think maybe it's still supersymmetric.
Yeah, because Seeley's method can only be applied to the case that the equation of motion, the unshared loci are the constant maps. That is.
Yeah. That's also the case here. So
that is supersymmetric. Yeah. Okay. I see.
Yeah. I think that's supersymmetric. But so the thing that I want to raise is in this theorem 2, actually we can also, of course, we can apply the construction to get a solution of the quantum mass equation. And the interesting thing is the solution you get is what we call one loop exact. So if you compute the path integral for the trace of the theory, which is the partition function. If you compute the partition function as a path integral, you just see trees or one loop graphs in the expansion. You don't see higher loops.
Higher loops vanish.
Yeah, all vanish.
But
so
you are talking about
that's quite interesting, but we don't quite know what that means.
So in your theory, you have an action. You can actually write down some action.
Yes.
Okay, no problem.
Well, but that's the old story in the paper of Seeley, Chinley, and Grady.
Yes, I see. Okay.
Um,
I'll hide myself.
Bye-bye.
Bye-bye.
any other question? Can I see the last slide?
Oh, yes. This one?
No, page 19. Do you have 19?
19 is thank you.
Oh, okay. I thought I thought there was one. Okay.
Yeah, thank you very much for your attention.
Okay. Okay, so if there are no question, let's thank the speaker again. By whatever.
Thank you very much.
I will switch off the recording and leave